Now let's look at some reactions that involve oxidizing alcohols. So oxidation reactions, we start with an alcohol and we'll end with a different functional group. So here's an example. This is 2-pentanol. And then an oxidizing agent could be sodium to dichromate. Then we also need an acid, an aqueous solution. This is an oxidizing agent, this combination of reactants. Then we would end with a ketone. So this is 2-pentanone. So if you remember from the previous video, the oxidation state of the carbon bonded to oxygen in a ketone is higher, so it's a higher oxidation state than its oxidation state in the alcohol in 2-pentanol. So this is an oxidation reaction because we're oxidizing that carbon. So let's look at some patterns here. We have a secondary alcohol here. We have an oxidizing agent. And we end with a ketone. Ketone is a specific functional group. And here's a little nomenclature note. For a ketone, the suffix is -one, O-N-E. So we can see that here. 2-pentanone, we have a pentane chain at carbon 2. There is a ketone functional group, that carbonyl. So we have 2-pentanone. Okay, so anytime you start with a secondary alcohol and add an oxidizing agent, we have a ketone as the product. Essentially, the carbon to oxygen, the OH bond, becomes a double bond between the carbon and the oxygen, and we lose the hydrogen. So there is a number of different oxidizing agents. Let's write this down here. And they're all in this list: chromium, in a +6 oxidation state. Metals can have really high oxidation states. So we have 3 examples. One is chromate, which is Cr O4 2-, plus a strong acid. We can have dichromate, which is what I showed above, in the reaction with 2-pentanol. Plus a strong acid. Or we can have chromium trioxide and pyridine. pyridine is a 6-membered ring, looks like benzene, but one of the carbons is a nitrogen. So I'll draw that kind of small right here. Okay, so that's pyridine. So all three of these are possible oxidizing agents. And in the example with 2-pentanol, we use dichromate and H2SO4 as the strong acid. Let's look at an example with a primary alcohol. So let's look at butanol. And then we'll use dichromate again. The spectator ion can also be potassium. So here's potassium dichromate. And then above I wrote H2SO4 in an aqueous solution. Down here, I'm writing the same thing, but just emphasizing that there's water. So we'll write H2SO4 and H2O. It means the same thing as writing H2SO4 and then parentheses AQ, which tells us that it's aqueous. So if we have a primary alcohol, oxidizing agent, according to the pattern we saw above, we would expect to replace that carbon to oxygen single bond with a double bond. So if we do that, have double bond, 4 carbons, and I'm just going to emphasize that there is also a hydrogen bonded to that carbon. So this is butanol, because this is an aldehyde. So the suffix for aldehydes is Al. But when we have a primary alcohol in a reaction, in an oxidizing reaction where there is water present, so this is why I emphasize the water, the reaction continues to then produce a carboxylic acid. The aldehyde typically is not isolated. It will just immediately continue and produce that carboxylic acid. If we want to stop at the aldehyde, we must use a different set of reagent. We can't use the chromate reagents or the chromium reagents. So when water is present, when H2O is present, aldehydes further oxidize to carboxylic acids. So I said earlier, like a few seconds ago, that if we want to stop at the aldehyde, we can't use the reagents with chromium. That statement is wrong. We just can't use the reagents where water is present. So the strong acids that are aqueous, having the water present, causes a reaction to continue. So to represent this chemically, we have the same reagent still present. I'm going to write another arrow to show that the carboxylic acid product. We end up with the carboxylic acid, where instead of a hydrogen being bonded to the oxidized carbon, we have an OH group bonded there. Adding to the blue writing down here, we have the aldehyde. We add oxidation or oxidizing agent. And we continue to the carboxylic acid. This is butanoic acid. So for a carboxylic acid, suffix is oic acid. Okay, so if we start with a primary alcohol and we add the oxidizing agents that have the strong aqueous acid, we end with a carboxylic acid. But if we use the chromium trioxide and pyridine, a non-aqueous strong acid, in a non-aqueous solvent, then we can end the reaction at an aldehyde. So here's an example of that. We'll start with butanol again. We can add chromium trioxide, pyridine, and HCl in a dichloromethane solution, CH2Cl2, and we end with the aldehyde. Because there is no water present, the reaction ends here at the aldehyde. Now this group of reagents, the chromium trioxide, pyridine, and HCl, is referred to as PCC, which is short for pyridinium chlorochromate. I want you all to be able to remember what PCC is and recognize this set of reagents. If you see CrO3, pyridine, HCl, CH2Cl2, I don't necessarily expect you all to remember this full name. Usually we don't represent these reagents by writing out the full name. We'd either write PCC or write out the specific molecules in the molecular representation. Okay, one more set of reagents that I want to review, and then we'll be done for these oxidizing reactions. Here's another example if we have a primary alcohol. We'll do pentanol, kind of change it up from butanol. We can add reagents K, potassium, MnO4, and sodium hydroxide, so a basic solution. These reagents produce an anion, a carboxylate anion. So we have 5 carbons. Carbon to oxygen bond is now a double bond to an oxygen. And then we have a bond from that carbon to a negatively charged oxygen. So this is the carboxylate anion. And then to end in a neutral carboxylic acid, we have to add an acid to solution to protonate that negatively charged oxygen. So in a second step, we add H3O plus or some acid. And we end with the carboxylic acid. So this has to occur in 2 different steps, because if we need basic solution for the first step and we need acidic solution for the second step. If we were to add the acid base together, they would react with each other and not produce the products that we are hoping for. Okay, so those are all of the oxidizing agents that we'll discuss. You might notice we haven't talked about any mechanisms. I will post what the mechanisms look like in our Top Hat folder, but these are not mechanisms that you'll need to remember for the class. The goal is to be able to recognize oxidizing agents, looking at the starting material and the oxidizing agent. Will you end with a ketone, an aldehyde, or a carboxylic acid?